In this class, we're going to consider volumes of revolution around the x-axis. So the formula for this, which we looked at in the previous class, is the volume of revolution is given by pi times the integral between the limits a and b of the function y squared dx. One of the challenges with this topic is not so much processing the integral, because we've already done quite a lot of definite integrals by now, so you should be quite competent with that part. It's the fact that you can get muddled between this being an x or a y and this being an x or a y. So when we come to look at volumes of revolution around the y-axis, these basically get changed around and you're integrating dy, because you're stacking the little cylinders that we looked at in the derivation of the formula in the previous class. You're stacking them vertically, so you're stacking them dy rather than dx. So if you don't have a formula sheet and you've got to memorize this, it can be easy to get the two of them muddled. So you need to work enough practice questions, or just think about it logically, thinking whether you're stacking them up the way, up and down the way, or along the way to whether to make it dx or dy. And if it's a y, sorry, if it's an x here, it'll be a y here. If it's a y here, it'll be an x here. So the two would never go together. Okay, so we're basically just going to use this formula and we're going to apply it to these two examples here. So we've got the functions and we've also got the limits. So this is the limits a and b for these two particular volumes of revolution. Sometimes you'll get a diagram in these questions, sometimes not. You don't necessarily need a diagram. You can, if you've got enough information, you can just plug it straight into the formula. Just to show you what this one actually looks like though, this is just a parabolic function, well, a parabolic graph, a quadratic function. It's going to be quite steep because it's got a 10 in front. So this guy would look something like, it's actually a very simple parabola because it's centered at 0, 0. It's got the turning point at 0, 0. So it's going to be a parabola, but it's going to be very, very steep. So rather than be that usual kind of U shape, it's going to be more, I guess, something like, probably like that. Now we're integrating between 0 and 2. So 2 would be over, I guess, like say here somewhere. So if you imagine taking a construction line up from 2 up to like there, and then if you take that sort of area there, and then imagine like spinning that around the x-axis to generate your volume of revolution then. Or you could imagine just taking the curve, that part there, up to just the point where it's at 2, and spinning that part around, and you're going to get some funky looking shape. And if you've got a 3D calculator or a 3D graphing utility or something like that, you could actually go ahead maybe and model that and see what it looks like as a 3D shape. My artistic ability does not extend far enough to be able to draw that, but it would be some kind of shape in 3D. But we don't really need to worry about the graph. We can just take the information and plug it into the formula. So our volume is going to be given by pi times, so the pi can either exist outside or inside the integral. Because it's a constant, probably best to take it outside. It's going to be the integral between 0 and 2 of y squared. You've got to be careful with the squared. A lot of students will just plug the y straight in, but we've got to square the y. So that's going to be 10x squared. So remember, although it's written as y, we're integrating dx. So we can only integrate dx if the terms in here are x's, not y's. So we're saying that the formula is y squared, but y is 10x squared. So it's the x version of the y we need to use. So basically just plugging in your function in here, and we're squaring that. So y squared dx. So just taking this forward, to tidy it up before we integrate, we could just go ahead and square first of all. So the integral between, or pi times the integral between 0 and 2 of 10 squared is 100, so it's going to be 100x squared is x to the power of 4. Okay, so it comes out like that. You could pull the 100 through the integral sign as well. That's probably a good idea. So that's going to be 100 pi times the integral between 0 and 2 of x to the 4 dx. Okay, so I might actually just pull this one over here to make some space. So that volume is then going to be 100 pi. You'll quite often end up with like some number times pi in front of your integral. That's fairly common in these. This is in a form that can be integrated using the power rule. So we're just going to increase the power by 1. So that's going to be x to the 5 and divide that by 5. So I'm just going to write that as 1/5 x to the 5, or you could write it as x to the 5 over 5. Either way is fine. And then integrating that between 0 and 2, so the limits are 0 and 2. So this then gives us 100 pi. Sometimes these will be calculator questions, sometimes not. Quite often they'll ask you to write your answer in terms of pi, which means basically leave the pi there. Or if it's a decimal version, you could use 3.14 or just use the pi button on the calculator. But before we get to that, we need to process this a little further. So we need to sub in our 2 first of all. So 2 to the power of 5 is 32. So it's going to be 32 over 5. And then if we sub the 0 in there, you're just going to get 0. So it becomes minus 0. So we're going to get 100 pi multiplied by 32 over 5. Now 100 divided by 5 is 20. So just thinking about the best way to do this, maybe 100 divided by 5 would be a good way to do it. So 100 divided by 5 is 20. So that's going to become 20 pi times 32. 2 times 32 is 64. So it's going to become 64, but putting a 0 on because it's not really 2 times 32. It's actually 20 times 32. So it's going to become 640 pi. And then, like I say, that would be acceptable as a final answer, or you could go ahead and use the calculator and get that as a decimal. Either way is fine. But because it's a volume, it's going to be units cubed because it's a 3-dimensional volume that we've figured out. So that's the process. Basically, just plug in the function and the limits into the formula and then working your way through. And they look a little odd, these at first, because they've got this pi that gets carried all the way through the calculation. So visually, it might take you a while to get used to these. They do look a little, they kind of jar on your brain a little at first. Okay, right, so that's that one. Let's move our attention over to the second example. So maybe again, just quickly to sketch the graph here. I'm not going to spend too much time on the graph. We don't really need it, like I've said already. This one, the function y equals the square root of x, looks something like this. Okay, so again, you can always use a graphing utility to check these out. So we're integrating between 2 and 10. So let's say that 2 is there, 10 is there. So if you were to put on, again, your little construction lines, think about spinning that area around the x-axis to get your volume of revolution, making it into a 3D shape, and it's that volume that we're looking for. So our volume, again, just plugging into the formula, is going to be equal to pi times the integral between 2 and 10 of y, which is the square root of x squared, because the formula, remember, has got the squared in it, dx. So this one's quite convenient because the square root squared, well, the square root and the square just cancel each other, so you just get the integral between 2 and 10 of x dx. And just carrying that one forward, that's already in the correct format to use the power rule for integration. So just leaving the pi in front, integral. Oh, in fact, I don't need that anymore because we can go ahead and integrate. So just integrating the x, we're going to get increase the power by 1, so it goes up to a power of 2, divided by 2, so it would be 1/2 x squared or x squared over 2. Either way, again, is fine. So we've set it up just like that. So now we just need to process the numeracy, basically. Be careful with the numeracy. It's easy to make little slips. This is quite a simple function, so was that one. They can be a lot more complex, so just be careful with that. You quite often see these as well with sine and cosine in them. So if you've got to sub in sine and cosine, values into sine and cosine, maybe some multiple or some version of pi in your limits as well, be more careful with those. So this is going to become pi times, so subbing in the 10 first, 10 squared is obviously 100, 1/2 of 100 is 50, and then 2 squared is 4, divided by 2 is 2, so we're taking away 2 like that, so 50 minus 2, 48, times pi is just going to be 48 pi, and again, volume, so it's going to be units cubed. Usually with finding areas or volumes with integration, we don't actually know the units. Like there's no units in the question because there's no units associated with a function or with the x and y axis in general. So we just write units cubed generally, or units squared if it's an area question. So that one, 48 pi, this one, 640 pi. So this looks to be a much larger area or volume than this one. So again, if you needed to work out a decimal version, you would just stick this in the calculator and get your decimal version of that answer. So that's basically how we use the formula for finding the volume of revolution around the x-axis. In the next class, we're going to do a very similar thing. We're just going to think about spinning them around the y-axis instead. One little thing to be aware of that I didn't have in an example here, but let's say that this function was given to you not in this format, but if you imagine squaring both sides of that function, you would get y squared equals x. Now sometimes they'll do this in questions where even though you need y to be squared, they'll give you the formula in terms of x as the subject, so you need to rearrange that formula. So imagine we never had this. Imagine they gave you that. You would then need to rearrange that. Well, in this case, it's fairly trivial. You would just take the square root of both sides to then make y the subject of the formula. They could do that here as well. So if we rearranged that for x, we would have y over 10 square rooted. They could present that original function that way. So it's not explicitly in terms of y equals, it's implicitly set like that. So you would need to rearrange that first of all to y equals, so you would turn that into that before you can then plug that part into the formula. That sometimes happens, you'll maybe see that in your practice questions. So when you're ready, just move to the next class where we apply this the other way around the y-axis.